Welcome everyone to the second Thursday session, and please join me in welcoming Trent to stage.
So I've got a bit of a fun story this morning that comes from my work as a sustaining engineer at Canonical. We support various Ubuntu installations, including OpenStack and Ceph installations. And this was one of the more, I guess I could say, interesting or challenging customer cases where I kind of had to debug from the top of the stack to the bottom of the stack and use some tools to get insight at all those layers. And so I thought it would be a good story to share with everyone, and hopefully you'll have some learning about some of the tools or the techniques or, in fact, the actual problem that I solved along the way. So starting out with what was the situation? Well, we had a user complaint that had an OpenStack cloud that was backed by Ceph storage. And this cloud predominantly had Windows instances, which is a little different to most of the environments we work on tend to have Linux instances inside of the cloud, or at least they'll have some Windows, but a lot of Linux. And this cloud was almost entirely all Windows instances. And their general complaint was that the guest performance was slow. If they clicked on the start menu or opened the task manager, that would take 5+ seconds. And that wasn't really acceptable, and I could see that, they showed me. And they also had another good metric was that when you first boot a Windows image, it does like a first boot kind of setup process, and it reboots itself and installs Windows updates. And that used to take maybe 5-10 minutes, and now it was taking 20-40+ minutes for that to complete. So something was obviously wrong in this environment. The other thing we tend to see was inside of the task manager and the resource monitor, the I/O utilization was often showing as like 100%, or we would see very high I/O latency inside of the VM. So as a brief sort of introduction to Ceph, Ceph is really great and interesting technology in itself, and I'm not going to go really at all in depth into how that works, but I will give us a few details just to understand the context. So Ceph is a distributed storage solution, and it tends to work with a number of servers, each of which having many hard disks, which we call an OSD, or Object Storage Daemon. And fundamentally, the interface that Ceph provides is an object store. So you can store any number of objects that have an alphanumeric name, and it will then choose to store those objects on one of those OSD hard drives in your Ceph installation across multiple servers. And obviously does that in a way that's distributed, highly available, and redundant. One of the important details to look at is that when we do a read or a write in Ceph, the client sends that write to the primary OSD for that object. And so in the Rados block device, which is what we're talking about today, Ceph also provides a object store interface, kind of like OpenStack Swift or Amazon S3, and it provides a POSIX file system called CephFS. All of these are built on that fundamental object storage interface, but we're going to be looking at the Rados block device specifically. And so what it does is it takes your hard disk of, say, 50 gigabytes, it splits it up into 4 megabyte chunks, and each of those 4 megabyte chunks sequentially in the disk becomes, disk object number 1, object number 2, object number 3, and so forth. And so when you do a write to your virtual disk in the VM, it figures out which one of those objects is the 4 megabyte chunk we're interested in, it finds which one of the disks that chunk has been assigned to, and it sends the write to that primary OSD. Now, we also want to ensure redundancy in the system, and so by default in Ceph, you'd set up a replicated storage with 3 replicas. And it's not the client that takes care of those 3 replicas, but instead the primary OSD. So the client sends the write to the primary OSD, and it's then responsible for sending it on to the secondary and tertiary copies to be stored. And it won't actually acknowledge back to the client the write is complete until at least 2 of those 3 writes have completed. So it must complete its local copy, plus at least one of the secondary or tertiaries needs to complete its copy, at least by default. Another little optimization we had in this cluster is it was a hard disk-based Ceph cluster, so it had about 240 hard disks in that cluster. But we also made use of NVMe SSDs as a journal. And so that optimization, the actual data wasn't stored on the journal, and it wasn't even cached on that journal. But what would happen as a crash safety mechanism so we could acknowledge writes faster, it would first write them to the SSD, tell the client it was done, and later write it back to the hard drive in usually the next 5 seconds or so. And that lets us just take advantage of the fact that often, particularly in online like database applications, they want that write to be acknowledged as quickly as possible in milliseconds rather than hundreds of milliseconds like a hard drive would normally respond in. But we can also take advantage of doing so many writes at once. Hard drives are quite good at doing parallel I/O, so we could do multiple hundreds of I/Os per second onto a hard drive, but only if we give them all to the hard drive at once. If we keep giving it a single I/O at once and saying we want that one done as fast as possible, we won't have as much throughput. So that's why that NVMe journal comes into play. So when I started looking at this particular problem, I started looking at some of the tools and performance counters that Ceph give us to kind of introspect the system, see how fast things are going, what are the latencies of the operations. And so the first tool I turned to is this command here, the Ceph daemon perf dump. And that gives us a whole bunch of performance counters we can look at. And it didn't really matter which of these I looked at, and what they are doesn't really matter too much, but all of them were showing very good numbers. So at most I was seeing maybe 100 milliseconds was the latency of what it thought all of the I/O operations were taking on average, and 100 milliseconds would have been okay. That's much better than we were seeing inside of the VMs. And in fact, most of the latencies it shows were much better than that. They were single-digit milliseconds or less. And so this was confusing to me because clearly inside of the VM, that's not the experience the VM was getting. We were clearly seeing operations that were taking hundreds, if not multiple seconds to complete. So that was a bit strange. In that same perf dump output, Ceph has a number of throttles, and these are designed to stop one part of the system overwhelming the other. Because it's such a distributed system with so many clients and so many disks, you don't really want to have anything bunching up in one particular spot in the system. And so to combat that, Ceph has various throttles in various layers of the systems, from how many bytes per second are being sent in by each client, to how many operations per second, to how much outstanding data for any individual hard disk can be outstanding. And if any of those throttles are exceeded, it'll push back on the system all the way up the chain to try and stop any of them just getting full or overloaded. So I also checked all these throttles. This is an example of such a throttle we can see here. And the way Ceph kind of tells us about these throttles is it says how many times we hit the throttle. So in this case, we've hit it 8 times, which is basically nothing. And then how much time it spent in total, how much it held back the system. So in this case, we can just take that time, divide it by 8, and we can see in this particular throttle example, it basically never held up any time at all. So in some systems I've seen, we might have had one of these throttles being exceeded, and we might have spent literally a half a second per transaction waiting intentionally, but that wasn't the case here. All the throttles were completely fine as well. So that seemed a little strange given the terrible performance of the system. Another tool that Ceph gives us is the ability to introspect all of the operations that are in flight in the system right now. So I can go to any individual Ceph OSD disk, do this dump ops in flight command. It will actually print out all of the operations in flight right now, and actually shows me each of the steps that operation has gotten up to and at what time that step happened. And so theoretically, if we've got operations that are taking multiple seconds, I should be able to look at this dump ops in flight, see an operation that's maybe 3 seconds old, and then see at what step it got stuck, which step took a long time. And I had a couple of problems really interpreting this data in this environment. The first one was that all of these timestamps are actual timestamps. You'll notice that it's not a differential time. So each step that we step through, from queued for PG to reach PG to started, all of those have an individual timestamp. So I'm sitting there trying to diff the time in my head, and I'm trying to do this not only for the 20 steps in this transaction, but for 200 other transactions that were going on in that 1 second on that one hard drive out of 220 hard drives on 50 servers. That turned out to be a little bit difficult. Now, originally I thought that might have been easy because the system was so slow. I thought everything must be running slow, but that didn't really pan out for me. The other difficulty we had in this particular operation I put on the screen, if you look at all the timestamps, they're all within about 0.1 of a second. So it got 99% of the way through this operation in 0.1 of a second, which is a pretty good time. But what I can tell this by omission rather than what's actually on the screen is that all of this stuff happened in 0.1 of a second, but the age up here, it says it's 2.8 seconds old. So this operation is still sitting here for 2.8 seconds for some reason on something. And what it's actually waiting for is, so op commit is when the operation was committed locally on this OSD, and sub op commit rec means that the secondary OSD number 133, it's also committed. But what we don't yet have is the subop commit rec from the tertiary OSD number 231. And so I can actually tell from this output that we're actually waiting for the tertiary OSD to complete the write in this case, and we've been waiting nearly 3 seconds. And that's certainly unusual. But the problem I had was then I wanted to go to OSD number 233 and find that operation in flight and see why it was stuck. And because there was no centralized kind of view for this, I had to ask each OSD for dump hops in flight. Even if I scripted that and did every OSD and every host in parallel, 99% of the time I couldn't get the two operations slow to match up, and I couldn't find them. So this approach clearly wasn't working very well, and I had to do something new. And so what I really wanted to do was find the outliers. So it seemed that most of the data I was looking at, everything seemed fine. Every so often I'd find one slow one, but then I couldn't correlate it with anything. So I set out to build an automated process to find these outliers for me, because there was no tool existing I could find that would actually do that, which did surprise me somewhat that I couldn't find anything other people had done for this. So I set out to write something on my own, and I used my knowledge of Ruby, which is my favorite programming language, but it really doesn't matter what you would use. And Ceph has some great debug logging options, and so I told it I wanted to do debug FileStore level 10, and it would then output every single operation in the system. It would output when it started and a whole bunch of steps, and at the end in a big log file that I could then parse afterwards. So instead of trying to capture everything by running that dump ops in flight, I'd instead instructed the cluster to dump every operation on every OSD in the entire cluster to the disk. I'd do that for about 10 minutes and then collect all those logs and process them afterwards. And this led to some interesting insights. So in this particular example on screen, I would look in the log for 3 log lines for the same operation. So for each operation that would have an ID number, so I could correlate the different lines. And there were 3 lines I found. So the first one was this line that would have do op in it. And so this basically meant that the operation had made it through all of the buffers and queues in Ceph, and it was about to be written to the disk inside of FileStore, which is the older Ceph storage mechanism. It then had another line where it would say the word write, and that actually meant that the write had been completed. It was actually sent into the operating system to be put on the disk. And it would also tell us the offset of the write, so the 3882496 is how far into the disk, and the 16384 is the size of that write. And then it also had a third line called the finisher line, which literally I was just matching for the word finisher. And after it's done a write, Ceph sort of puts it in a queue to kind of just clean it up and actually complete the operation. And in some environments, that can be a bottleneck. It wasn't in this case. But what I did do is I parsed those 2 timestamps, and I've printed in this first column, 2.13. It took 2.13 seconds to get from when it started to do the operation to when it actually finished sending that operation into the Linux kernel to be put onto the disk. And so this was clearly an outlier in terms of time taken. And if I looked at the Ceph code about what would happen between those 2 log lines, it was actually a very small amount of code. And so that was a function called FileStore write, and pretty much all it did was send the data to the kernel to be written. It didn't do much else. There was no locking and throttles or queuing. So that was kind of surprising. And then the other thing I looked at was I counted for the number of operations. I processed every operation in the whole cluster within that 8-minute time period. And the ones that took more than 0.1 of a second was only 1.4%, about 1,800 out of 122,000 operations, which is actually a really small number and explains why I was having trouble finding them manually in all the outputs, because only 1.4% of the items I would pick at random would really be slow in reality. The other thing that was kind of interesting is that Ceph does all of these operations in only 2 threads. It's not particularly parallelized, and I found that of these 1.4% of operations, we had 2 threads and 500 seconds of time to complete all of those operations. So in fact, we had 1,000 seconds of CPU time, and we spent 400 of those seconds on those 1.4% of operations. And so for those 400 seconds, because we only had 2 threads, the whole other queue of operations was actually blocked up behind us. So not only were these actually slow operations slow, it was then causing all of the operations that would have been fast to also be slow because they were waiting in a queue. And so that was also really surprising to me that nearly half of our time was spent on 1% of the operations, and that those were really, really slow. They were taking multiple seconds. We would expect that it should take less than that. I also wrote a tool to parse that dump ops in flight and to pull out the differential time between different steps, so from initiated to commit sent or from initiated to reach PG, and to print out those times And that made that a lot easier to parse, although it didn't end up being super relevant to the case in the end. But it did make that data a lot easier to consume. So those tools are on GitHub if anyone would find those useful. And really what I learned for this is it's easy to lie with statistics. Or more importantly, the statistics are not lying to you, but they're probably misleading you. And so even manually looking at log files really wasn't helping me, and I needed to actually look at all of the outliers, or preferably like a histogram of operation latencies, and not rely on the averages, because the averages were beautiful. They matched what I'd see in a normal system, but they weren't really telling me what was happening in the system. So now that I knew that I had this 1.4% of operations, and that I knew that they were taking a long time, specifically in this FileStore write call, I set out to understand why that was happening. And so my tool of choice for that is perf. And perf is an incredibly complex and wonderful tool from the kernel that lets us profile the system. And I'm sort of using it in its most simple form here, where I'm just asking it 1,000 times a second. I want to know what code is executing on the system. And from that, I can determine how much time we're spending in each function, and maybe figure out which function is slow, and then look at that function and figure out why is that function slow. So the way that we do that is we use the perf record call. We basically tell it which process ID we want to inspect. It is possible also to sample the entire system with -a instead of per process, but it's a little bit easier to consume the output if you look at a per process. And we also tell it to use a frequency of 997 times per second, and that sounds like a strange number, but the idea behind that is that we don't want to accidentally coalesce with some kind of timed event. So if Ceph is doing something every 1 second, or every 100 milliseconds, or every 1 millisecond, if we scheduled the samples at 1,000 times per second, we might accidentally line up with those timers. So to try and avoid that, we just offset the time a little bit by an odd number, just to avoid accidentally sampling the wrong thing. We then tell it to sleep for 11 minutes, so that just means I want to get 11 minutes worth of data. And this will give us a raw data file back. So perf outputs a perf.data file, and you can process that with the perf tool itself. It has some command line sort of output that you can look at. But far and away, the easiest way to consume it visually is with something called a Flamegraph, which looks like this. And Flamegraphs were popularized by Brendan Gregg, but have been used in all sorts of places. And the idea is that along the x-axis, along the bottom, we have time. So for the width of anything on the screen, it's how much time within that sample it took up. So say we sampled 1,000 times. This particular item here that takes up about half the space, that means of those 1,000 times we sampled, we saw that particular item, half of that time approximately. And then on the y-axis going up, we have the call stack. So starting at the bottom is the function that we started in, and then the function it called, and so on down the stack. And so from this, we can visually kind of see what was taking up a lot of time. We're not trying to process numbers. Looking at numbers on a screen is never a productive exercise, which we learnt earlier. And the other thing about these flame graphs that's great is we can zoom in. So for example, about half of this flame graph is the thread called TP, OSD-TP. That's the OSD thread pool. That's actually not the one we're interested in. We're interested in this one called TP FStore ops. That's the one that's doing all the FileStore code we found to be slow. But it's this small bit of the screen, and we can't really see that. But when you open the SVG in your web browser, you can click on that and you can zoom in. And so now we can see the entire FileStore thread pool, and we can actually now start to make out some of the detail in this graph. Looking at this graph, we see kind of 3 big chunks of time being taken. So sort of on the left, this is just a bunch of noise, stuff that's not running very often. We can probably ignore it. We see about half of our time is taken up inside of this, which is just the thread pool worker. And it seems to spend most of that time waiting for a lock. We also see inside of the FileStore do-op, it's also spending time here waiting for a lock. But the interesting one turns out to be this one on the right. So we spend about a quarter of our time inside of Ceph buffer list write, which is basically when it takes the data and sends it into the kernel, which is exactly what we saw earlier was being slow. And so it's executing a system call called pwrite v64. And that's literally the same as the write system call, but instead of doing one write to one file at one offset with one set of data, we give it a list of writes. So with one system call, we can tell the kernel to write 100 things instead of just one. Now this call stack has a whole bunch of functions with names that may or may not kind of make sense. They didn't really make sense to me, so I set out to read the Linux source code to understand what it was actually doing, what were we spending time on. And what I found is right up the top, there is a function called out of line wait on bit. And if you read the source for that, it has a comment that said, if we issued read requests, let them complete. We'll wait for them. And it really wasn't immediately obvious, but through a bit more reading of the source, what I determined was that the write coming in from Ceph was a write that was less than 4 kilobytes. And inside of Linux, in the page cache, whenever it caches data being written to a disk, it can only keep track of data in 4 kilobyte increments, or 4,096 bytes. And so if we made a write that was smaller than 4,096 bytes, it actually had to read the rest of that 4 kilobytes off the disk, modify the small part that we changed, and then it could put that into the page cache to then be written back to the disk later. And so what I found was basically that Ceph was sending these writes smaller than 4 kilobytes. The kernel isn't capable of representing that in memory. It can't cache that write. And so normally when Ceph does one of these writes, 99% of the time it's a buffered write. So it just gets stored in the page cache in memory, returns back to Ceph very quickly. The disk is not involved at all. But because we're doing these unaligned writes of less than 4 kilobytes, we had to actually wait for the disk to read the rest of that 4 kilobytes before it could continue on. And if you remember, we only had 2 threads that were doing this. So every time we got stuck doing this, everything was waiting for that item to come off the disk, and the whole entire Ceph queue of operations was getting stuck up behind that. And so why did this turn out to be a problem? Well, let's review how FileStore works in Ceph. So the first thing it does, we've split the entire disk up into 4 megabyte chunks. And when an operation comes in Ceph, it actually locks that entire 4 megabyte chunk before it starts to work on it. And so now, even operations that are for a different part of the disk, we might only be writing to, say, 1 megabyte of that 4 megabyte chunk. If another operation comes in for a different 1 megabyte, it still gets held up by this lock. We then write that operation out to the NVMe journal, and then we do that pewrite v64 operation to put it into the page cache in memory in the kernel. And Ceph is basically using the kernel's page cache as like the authoritative store of information. So it's not expecting the kernel to actually write that data to disk right now. That'll get done much later. It just wants to put it in memory in the kernel for being written later. After it's done that, then it unlocks the 4 megabyte chunk. It acknowledges the write to the client, and it sets out about actually flushing that write to the disk later. And so this was really why the problem was even worse than it appeared, because not only were we blocking writes to the specific bit of data that we were working on, we were blocking writes to the whole 4 megabytes around it. And I found in practice with the way the VMs were behaving, they were very, very often making individual writes, multiple writes to the same small area of disk. And so that was really just exacerbating the problem. So let's have a look at how that looks visually. So I actually went back and augmented that tool I told you about earlier, where I parsed all the log lines to see how long each operation was taking. And if you recall, it also told us the offset of the operation. So in this case, 388.2496, that's how many bytes into the disk we were writing to, and the size of it, 16.384. And so I augmented the tool to calculate whether that write was going to be an unaligned write. Was it aligned to a 4 kilobyte boundary, or was it not aligned? And so we can just do some simple math. So we can take the offset into the disk and divide it by 4,096. And if we had an even number, that means it is aligned to 4,096 byte increments, so it's in 4K chunks. But because it's not, you'll see it's an odd number, 947.875. That means our write is offset. It's not in a 4 kilobyte chunk. It starts partway into a 4 kilobyte chunk. And we can see that visually here. So at the start, we don't have this data. This data is missing, the little bit in red. But we have all the green data all the way through to the end. And then in the last 4 kilobyte chunk, we only have the very start. So we're missing the end of it. And so for this particular write, we actually don't have to go to the disk once. We have to go to the disk twice. For both the first 4 kilobyte chunk and the last 4 kilobyte chunk, we have to read from the disk that missing data to fill it in. And that has to be done at the time that write was happening. There's no way to defer that. And the reason for that, again, is that the Linux page cache has no ability to mark data dirty in any less of an increment than 4 kilobytes. So if it deferred it to later, if another write came in for that same bit of data, it wouldn't know how to deal with that. We've got a different example down the bottom here where the offset that it starts at, which is 1916928, that is divisible by 4096. So the offset is aligned by 4 kilobytes, but the amount of data we sent is only 7168, which is not divisible by 4096, and so we're still missing the last little chunk of data in red. And so in both of these cases, we hit this problem. And that actually turned out, so once I augmented my script, you remember we had 1800 out of 122,000 operations that were slow, all 1,800 of those operations were partial writes, every single one. And that really surprised me. I kind of expected them to be correlated roughly, but I didn't expect it to be literally every single one. And so now I knew we had these slow operations. I knew why, because of these unaligned writes. And so I set out to say, well, how can we fix this problem? So the first thing I tried was to increase the number of threads that we were processing all the writes with from the 2 by default to 32. And I thought, even though we were still going to get hung up, at least it was doing a bunch more in parallel, so we wouldn't be holding everything up as much. Unfortunately, that helped like a little bit. Maybe like it got 20% better, but it really was not anywhere near better enough to actually make a meaningful impact for the customer. So that was possible fix number 1 that didn't work. At that point, though, because I now knew about these unaligned writes, I thought maybe rather than just reproducing this in the customer environment, I could actually reproduce this myself in a test environment. And I was able to do that with some further surprising findings. So the first one I found was that I could get rid of the VM. I didn't need to use QEMU or a VM anymore. I could just use the Ceph RBD client. It has a built-in mini benchmark tool. It's pretty simple, but I could ask it to do 512 byte-sized writes. And so I told it to simulate a 256 megabyte disk, simulate only 512 byte writes, and just do a whole bunch of them at once. And that reproduced the problem. What was surprising about that was it was only a 256 megabyte disk. I would have expected all of that data to fit in the RAM cache of all the nodes in my test cluster. And so it seemed really strange that, in a real environment, you have, terabytes of disks, but maybe only hundreds of gigabytes of RAM. So in a real environment, we could expect sometimes the data is not cached. But for this very simple test, we were writing a very small disk all at once. That should have been cached, but we were still hitting the problem. So that was surprising. And the other surprise was if I wrote a much larger disk, say a 100 gigabyte disk, I would have expected the page cache RAM usage of all the nodes to raise to match not only the 100 gig size of the disk, but the replicas. So I would have expected 3 times 100 gig of RAM usage. And I didn't see that. I only saw about 100 gig of RAM usage. So it seems like for some reason, not all copies of the data were staying in memory. They were being evicted from memory for some reason that at the time I did not understand. So I set out reading the Ceph source code to try and understand maybe why things were getting evicted from memory. Was it like a direct write or something weird going on? And it turns out that an optimization was added to Ceph to actually intentionally discard this data from the page cache. So if you remember earlier, when our write's going through the Ceph OSD, when we do a write, it comes into the primary and it's copied to the secondary and the tertiary OSDs. But when we service a read, that always comes to the primary OSD. It's never load balanced to the tertiary or secondary OSD. So those OSDs never need to read the data back under normal operation, only under a failure. So an optimization was added to Ceph to call madvise with the flag fadvise don't need to tell the kernel on the secondary and tertiaries only that we didn't need this data anymore, you could throw it away. And the idea behind this was to reduce the memory pressure on those secondary OSDs, so it would free up more RAM for caching data that was actually, because each OSD in Ceph is not just a primary or a secondary, it's primary for sort of a third of the data, and it's secondary and tertiary for 2/3 of the data. So each node is performing all roles at once. And so theoretically, that would reduce the memory pressure, but in this particular case of an unaligned write, what was happening is even if I wrote that 512 bytes at the start, and even 1 second later I wrote the next 512 bytes, it had already thrown that 4K chunk away and had to read it back from disk again. Even literally a second later, it didn't have to be minutes or hours later. So I discovered there was a flag for that in Ceph, and so I made a configuration change, and I told FileStore not to use fadvise, don't perform this optimization. And that actually resulted in a very significant performance improvement. So about 75% of the operations, slow operations went away. We only had about 25% left, so I guess you could say like 0.3% of operations. And I also found if I looked at IO stat for the underlying hard drives, previously the system was doing about 40 reads per second from all of the drives, servicing these unaligned writes, and that went down to 2 per second. So it was a dramatic decrease in the amount of data we were reading from the disks. And that also had a flow-on effect because now the disks weren't busy doing reads, they had much more time to spend doing the writes that they were supposed to be doing. So this really helped quite a lot. I would say the performance was now acceptable within the environment. It wasn't perfect, it could be a little better, but it was very usable now. But I thought, we could probably still do better than this. And so it turns out that 4K drives or disk storage devices that want 4K aligned I/O are nothing new. And in fact, hard drive manufacturers since 2010 have been moving towards this for real physical hard disks. The majority of hard drives you can buy now actually want these same 4096 byte aligned writes. And the reason for that is that internally on hard disks, the way data is stored on the platter is in it used to be in 512-byte chunks since the start of probably the 80s, I guess. And for each of those 512-byte chunks, it had like a little gap, a sink, an address, some like identification data. It would have the 512 bytes of data, and then it would have 50 bytes of error correction data. As we wanted to get hard drives to be denser and denser, that error correction data was taking up more and more space on the platter. And so what they wanted to do was move to drives which used data in chunks of 4096 bytes. They would use 100 bytes of error correction data, so half of it, and they would actually gain back about 10% of the space on the platter. And so this was being done by hard drive manufacturers about 2005 to 2010. Now, it turns out, however, because of wonderful legacy and compatibility, that we couldn't just change the hard drives to now report that they had logical block sizes of 4096 instead of 512, because that caused compatibility issues with all sorts of wonderful Microsoft software. And so no version of XP would support this. 2003, Vista, 2008, Windows 7, in the initial releases did not support it. That was added in service packs. But even if you had like the latest like Windows 10 service pack, Hyper-V and Microsoft Backup, of all things, would both store data internally inside of files based on the block size of the underlying file system, but never stored that block size inside the file. So if you even copied that file from a drive of one sector size to another sector size, the file would stop working. And that turned out to be a compatibility issue. So what the drive manufacturers did was they kept reporting a logical block size of 512 bytes, but they added this new special physical block size extension so it could tell the operating system the real sector size of 4096, and therefore ask the operating system to try as hard as possible to always send 4096 byte chunks of data because it's going to be faster. What we'd have to do, what those hard drives and what Ceph has to do is if it doesn't get all 4096 bytes, it can't calculate the CRC. So if you send all 4 kilobytes in at once, it can immediately calculate the error correction data for that, and in one stripe around the hard drive, it can write the data and the error correction data at once. But if you receive only a partial write of, say, 512 bytes, it cannot calculate the error correction data for the whole 4 kilobyte chunk. And so if it just wrote the 512 bytes, the error correction data would become invalid. And so what the hard drives have to do is actually first spin around to read the 4 kilobyte chunk, apply the 512 byte modification, calculate the new error correction, and then write the data back to the disk. That's what we would call a read, modify, write penalty. It's the exact same thing Ceph was in effect having to do. So most new drives do that, but so Windows and Linux and everything else has been augmented to understand this new physical block size kind of hint, and should therefore do less of this I/O that was causing us problems. So my hope was, well, let's tell Windows and the VirtIO drives on Windows that have physical block sizes 4096. So I set out to say, well, how can we do that? This is where the stack gets a bit exciting. So OpenStack, for its virtualization, uses QEMU, which is the emulator, but it's managed by libvirt, which is kind of like a layer for doing all the configuration. And then because this is an OpenStack cloud, we're using OpenStack Cinder to manage those volumes. So we really need support for this in OpenStack to configure libvirt, to configure QEMU. And so QEMU added support for this in 2010, which was great. Libvirt added support for this in 2012, which was great. But OpenStack Cinder, as of my working on this case, didn't have support for this. And so I actually had to add support, and there's a pull request for that I've linked there. So I patched Cinder to do this, and then I rebooted. We did a test VM. And what we found was that if we booted a Linux VM and we checked the logical and physical block sizes, it came back correct. So it said 512 logical, like it always did, 4096 for the physical. But when we did this on Windows, it didn't work. So it still reported a 512 byte block size. So something wasn't working. And it turns out that there was a bug in the VirtIO drivers, which it technically had support for this flag, but it wasn't working properly. And that bug was only fixed in July 2018. Which was in fact before I worked on this case, But the VirtIO drivers have a concept of a stable release and a latest release, and this particular bug fix wasn't in the stable release, and so it wasn't on the customer's machines. And bearing in mind they have like hundreds and thousands of VMs that all have this driver, and for other kind of complicated reasons, the VirtIO storage drivers are not in Windows Update. So most normal storage drivers would be in Windows Update, and those VMs would have updated them at some point. I think, and I'm not authoritative on this, but I think the reason the VirtIO driver is not in Windows Update is because the VirtIO PCI ID is a shared ID by like multiple companies. So like it's an open source thing, and like Red Hat have drivers, and Canonical have drivers, and various people have drivers. And so technically no one owns that ID and can really claim to own the driver update process at the, on the Windows side. And so no one does Windows Update for that. So that was a little bit of a problem. But if we upgraded the VirtIO driver to understand this physical block size, which was now fix number 5, that had a dramatic result. And so what I found if I ran the same test was that the number of partial 512 bytes were reduced from 23% of all writes during first boot and Windows Update to only 1.8%. And the number of, most of those happened during early boot, like in the very, very early boot phase, and so it didn't have a big performance impact. Another sort of interesting thing is this was particularly noticeable in this cluster because it was a hard drive-based cluster, even though we had that NVMe journal. If you had an all SSD or all flash cluster, this problem would be less noticeable, but it'd still be very much there. And so you would still be adding a lot more IOPS to your SSDs, and you would run out of capacity on them faster than you would have otherwise. But you probably wouldn't have experienced the desperate, 5 seconds for everything to happen kind of problem. And so I think this fix at all layers of the stack would be valuable even on all flash clusters, even if you're not noticing it quite as direly. Another thing worth noting, so as of right now, the OpenStack Cinder patch in order to expose the physical block size of 496 has not yet merged because I made it work only for the Ceph driver, but they want to make it work for everything, so I just need to, basically, it's a little change needed to fix that. But there's actually 2 ways of consuming Ceph disks in OpenStack. The first one is the OpenStack Nova service will directly get your disk from Ceph without involving the Cinder volume service. That still does not have support for this flag as of right now. It's only if you specifically request a volume from Cinder that comes from Ceph that it will work with the patch that I linked earlier. That's something that I'll probably look to address soon, assuming that that's easy to do. So the key takeaways really that I hope to sort of bring to you from this is that number 1, look for outliers and for histograms over averages. Averages are very misleading anywhere. And so they're great as a first start, but don't let them be any more than a first look. Ceph has actually added histograms in newer versions than what this customer was running, which is good in that I would at least see that some percentage of operations were running extra slow, but it still wouldn't have told me why. So I still would have had to create a tool like I did in order to parse the logs or use some kind of profiling to understand why they were slow, but I at least would have shown me earlier on that we were in fact being very slow. Writing custom tools is something you can easily do. The one that I wrote is just like 50 lines of Ruby. It's very, very simple. It just stashes everything into some like dictionaries as it reads through the log. I had to add some extra smarts because we have 2 threads at once in parallel. You have to sort of key off the thread ID, but it wasn't really that difficult. So don't be afraid to write some kind of custom tool in your favorite language or in awk or some kind of processing language to help you solve problems. It was very, very valuable. And if I hadn't have done that, it would have been, I think, very difficult to solve this case. Another thing that I didn't really talk about why, but I found in the course of this case and some other cases, it can be very misleading. Theoretically, you should be able to sample a subset of nodes, but in practice, I've found that to cause me to miss things quite often, and that if possible, I suggest analyzing every node in the whole system, or at least a significant number of, more like 20 or 50% than like a handful of nodes. Perf and Flamegraphs are very powerful. You can use them in all sorts of problems, so I suggest if that's something that's new to you, if you look at Brendan Gregg's resources on Flamegraphs and perf, that you can go a long way. And you can create Flamegraphs for other programming languages as well, Python and Java and all sorts of things. And last of all, remember to always test and verify your changes at all levels of the stack. If I had have just assumed that when I did that physical block size change, that Windows was correctly interpreting that and doing what it should be, I would have missed the fact that it wasn't. And so I might have assumed that things were as good as they were going to get. So whenever you do make a change, you should always try as hard as possible to actually verify that change had the intended effect. And so, for example, in this way, I did that not only by using the tool to check that the sector size was there, but I then also did another benchmark, analyzed the logs, and found that the partial writes were reduced. So I sort of verified in both ways that the change was doing what I expected. And so with that, that's all I have. The only other thing I would add is if these kind of problems sound interesting to you and you might be interested in working with me on this sort of stuff at Canonical, then feel free to have a chat to me. Otherwise, I think we've got about 5 minutes for questions.
Thank you, Trent.
The slides are also already online at that URL, so if you want to find any of the stuff that I wrote, you can just hit lafayette.net/talks, and the PDF's there as of now.
Do we have any questions? Well, here you go.
So what was the biggest red herring you sort of like, what was the worst wrong path you went down while investigating?
What was the worst wrong path I went down? I spent a lot of time at the start of the case constantly doing those performance counter dumps and the dump ops in flight and constantly trying to look at the ops in flight data to figure out where the operations were getting slow. The reason that turned out to be problematic is twofold. Number one, the slow operations only ever happened on the secondary OSD. And that had the flow-on effect of that there was a lot of noise in the data because I could see, well, the operations were slow on the primary. They were still there in the ops in flight because it was waiting on the secondary, but there was no reason it was slow. And so to then find the operation on the secondary OSD and why it was slow there didn't really happen, particularly because what tended to happen was the slow part would only log right at the end and then it disappears from that output. And so your window to capture that is actually quite small. So that was probably, I mean, I think I spent probably at least a couple weeks, like a week or two sort of on that data rather than where we ended up. And that really came down to that lack of automated processing. So I think automated processing, ideally would have come a little earlier.
Anyone else?
Presumably this was a version of Ceph that didn't support BlueStore?
So that's a good question. So Ceph actually had an old, this FileStore is an older method that Ceph used to store things where the data was stored in an XFS file system underneath. Newer versions of Ceph use a storage mechanism called BlueStore, which actually stores into raw block devices. However, and I forgot to mention this, so thank you for asking, it has the same problem because BlueStore checksums all of its data, unlike FileStore. And so in BlueStore, it checksums the data in 4K granularity, and so if you don't get a full 4K write, it has to then read the data from disk in order to checksum it. So I did find similar problems even on BlueStore, but you are right in that the version we were using here was Ceph Dual, which it technically had BlueStore, but it wasn't production ready. I did also note there's some documentation in the Ceph wiki that talks about handling partial writes specifically under BlueStore specifically, and it talks about a mode where it would cache that partial write until later that's not currently implemented. So someone's apparently thought about this problem at some point, but hasn't gone all the way to an implementation solution. But I think the 4896K sector size really is the ultimate solution. Once that's in place, you can turn off all the other changes I made because you just don't get those writes that often.
I think BlueStore would probably perform. Sorry, BlueStore would probably perform better, so you would get better performance. But yeah, the problem would still be there. But are you guys, you're supporting Joule? Like, obviously you are.
Right.
How long do you intend to support Joule for? So
Joule shipped with Ubuntu Xenia, which was 16.04, so we're, I think, heading towards 4 out of the 5-year support lifecycle for that. So it is heading out, but we're still finding BlueStore is still really maturing. For the block device, it's not too bad, but we've actually had a lot of problems with Rados Gateway with BlueStore, even in newer, Luminous Plus versions. And so it is still a little, depending on what you're using, we're still in a bit of a transition period, I think, between the two. It's also quite intensive to upgrade, even if you're on a newer version, to upgrade your existing OSDs from FileStore to BlueStore, you have to basically blow them away one at a time and resynchronize them. And so that's quite an intensive process in larger clusters to do. So we have people that are now doing that, but not everyone has done that as of yet. They've just chosen to stick with the status quo.
Last question, if anyone has one, raise your hand. All right, thank you, Trent.
Oh,
There's one more.
all right, we can talk after.
No? Okay.
All right, thank you very much. I hope that was informative.